diverge. Okay, which one of these three do we not have to worry about?
Diverge.
Absolutely.
No. This one. All right. We don't need to worry about conditional convergence in this case because every term here is positive. So it converges absolutely or it converges not at all, or it diverges. Conditional would only be if there were some positive, some negative terms. Okay, so we need some sort of convergence test. Anyone have a suggestion? Integral. Why the integral test?
Oh, it's easy. Okay.
Integral test, and you know that before even doing the problem because I'm just.
It
if you
satisfies all it needs.
What?
It satisfies the rules for integral test.
It satisfies the rules, yeah, and it's something that you can't integrate. So basically, if you recognize a function that you can't integrate, then the integral test will be helpful. Now you can integrate this because you can do u substitution, whatever you want it to be. Squared and 2x, and so we get 1 half e to the negative u. Oh.
Yeah, I was going to say that.
2x squared, or let's make that 2, and then that's 4, and that's 1/4. Then that's 1/4. Any other mistakes? Good, all right. So negative 1/4 e to negative 2x squared. And so now we're doing this integral from, say, 2 to infinity, or 1 to infinity, or whatever, from any number to infinity. Yes?
Was it k e to the 2x?
It's k e to the negative 2k squared. Is the
So why du 2k?
du, that's supposed to be a 4 now.
But there's no k.
No, this is supposed to be du is 4x.
So where do you get the extra?
Extra x.
It's k, it's not x.
Oh, so I'm changing the k's into x's. Right, this is something that we just did notationally. You could leave them as k's and say integral k e to the negative 2k squared dk, but I don't know, we always use x's with integrals.
It's k. So this is k.
This is a k.
Ah,
Ah, okay, yeah, this is a k. All right, so we want the limit as, let's say c approaches infinity, negative 1/4 e to the negative 2x squared from b to c. All right, limit. Plus 1/4 e to the negative 2b squared. And what is this limit?
E to the 2.
Or, I mean, if we started at 1, yeah, b is 1. But it's a finite number. So what does that tell us? Great. Yes?
You could do the first true false one.
Sure. The reason I was a minute late is I was looking all over my office for my copy of the practice exam.
You go back.
Um, partial sum of some series, we don't know what the series is given by this. Then the series is an, each term is 2 minus n over 3 to the n, so n greater than 1. Ideas. Let's say you haven't touched this yet. What might you do? Yeah.
Some short request for you real good.
What might you do? And really with any of these problems, yeah? Start writing some out, right? If you're stuck, just write out some terms. There's nothing that says you can't do that. What would A1 be? That's the statement about n greater than 1, but we can still write what A1 is. 2 over 3? How did you get that?
Oh, it's 2 minus 7. I thought it was 2 to the n over 3 to the n.
No. This is what we're thinking. This is what we think the formula for an might be. But we don't know. Did anyone tell me what A1 has to be? How did you get 1? Okay, well, A1 should be S1. But that would be 1 plus 1 over 3. 3/4. Can anyone tell me what A2 would be? What? S1 plus S2, yeah, I mean it's sorry, not plus. Right, A2 is S2 minus S1, right? S2 is A1 plus A2. We subtract A1 and we get just A2. So S2 is 1 plus 2/3, 1 plus 2/9. Should be 11/9. Minus 4/3. 11/9 minus 4/3, what is that? Okay, did I do that right? 1/9. Why isn't it negative? No, it is negative. It is negative. Okay. All right. So it is negative. So A2, is A2 equal to 2 minus 2 over 3 squared? No. Okay, this is false. We calculated what A2 is, and it's not that. You couldn't stop at A1 because this says for n greater than 1. Yeah.
Why do you subtract S1 minus 2?
So because S2 is A1 plus A2, S1 is A1, so S2 minus S1 equal this. Yeah. Oh yeah, we can move on to the next. Unless there are more questions on this one? What's up?
Do we do a,
Anyone have a specific Taylor series remainder thing they want to talk about? Yeah?
Fx is square root of x at a equals 16.
And we want to approximate what?
16.2.
With how many terms? terms or with our third
Order, third order.
third order?
And then it wants the remainder term, find an upper bound.
Okay. There we go. So, f of x is square root of x. So, how do you want to generate the Taylor series? Yeah.
You will have to find first derivative, second derivative, third derivative, and the fourth derivative.
Okay, let's do that. F is root x. F prime is 1/2 x makes 1/2. It's third order, but we'll need the fourth degree to do the remainder part. We might as well figure that out now. Negative 1/4 x to the negative 3 halves. 3/8 x to the negative 5 halves. Negative 15/16 x to the negative 7 halves. Okay. Any mistakes? Good. We will need the fourth derivative in order to do the remainder. So that's why I did it now. So we only need, the first three derivatives to do the Taylor polynomial. P3 of x. So what is it? At 16. Excellent. At a equals 16. So you guys tell me. First term. Second term. Okay. 16. Right? We plug 16 into the derivative. We should get 1/8. Third term. All right, we're going to get large powers of 2 now. Let's work through it. We plug in 16 here. We take the square root, that's 4, to the negative 3, that's that's 64, times 4, 256. Sound right? All right, so negative 1 over 256 divided by 2 factorial. So negative 1 over 512. X minus 16 squared. Okay, and then we need 4 to the 5th times 8 to the times 3 factorial. I don't want to do that for me. What? 2048. All right. 3. Is that divided by 3 factorial?
I think so. Or no.
Don't write that down yet. I'm not entirely sure of that. Okay. So I'm going to put a little note here. This should be f triple prime of 16 divided by 3 factorial. Maybe the numbers are not perfect. Maybe they are. I don't know. But there's our Taylor polynomial. And then what we say is that the square root of 16.2 is estimated by plugging 16.2 into the Taylor polynomial. And so you just run through this calculation. 4 plus 1/8 times 0.2 plus negative 1 over 512 times 0.2 squared plus, I think, 3 over 2048, 0.2 cubed.
I got it.
It's not 1/4.
It's not, okay. What is it?
I don't know.
I got 1 over 16,384.
I'm going to leave it blank for a while until
No,
2 people tell me the same
I
answer.
always check them out.
The number is not super important, and that's a plug into your calculator.
Oh, for sure. I end up getting this back.
Okay. So this equals some number, right? Calculator. Oh, I get too bogged down on the number here.
1 over 16,300.
16, 1 over 16,000 what?
384.
Do I have a second? Good enough for me. All right. That's what it is, we'll say. So 1 over 16,384. And so all this stuff, you know, you calculate or whatever it is, it's some number. And that's our approximation of the square root of 16.2. So it's going to be like 4.137, I don't know what it is. Any questions to that point? Yeah.
That fourth front taking care of the 16 back from
4 in front taking care of.
Why are we plugging 0.2 in?
Because we're plugging in 16 for x. So I just did 16.2 minus 16 in all of these. Other questions? Okay, so now the remainder part then, right? The remainder of this approximation is f to the fourth at some value c divided by 4 factorial times x minus 16 to the fourth. Actually, I can't even put in what x is. X in this case is 16.2 minus 16 to the fourth for some c between 16 and 16.2. Question?
Yes, because it's the upper limit, upper bound, you want C to be the number between 16.2 and 16 that'll give you the greatest value.
Exactly. Yeah. And there was a question right in front of you too?
Are we going to be given that equation or do we need to know it?
You need to know this. This is Taylor's theorem. I think I called it Taylor's theorem.
Isn't that just pretty much the next term?
And it's not hard to remember. It's just the next term. It's just the next term in the Taylor series. All right. So the remainder is this for some value of c. But like was just said, if we want an upper bound, we want to know. Let's see. The value. I don't know. I want another letter. I'll just use C. Fine. Of C between 16 and 16.2, for which f to the fourth of C is biggest. We want an upper bound, so we find where this fourth derivative is biggest, and if we just take that as the value, all the other values are smaller than it, so even though we don't know what C is, we know it's smaller than this. And the fourth derivative, unfortunately down, negative 15 16ths, x to the negative 7 halves, okay, where is this bigger? At 16 or at 16.2? Is this increasing or decreasing? All right, this is decreasing. So it's biggest at 16.
That's negative 15 over 262,000
So that's the biggest the derivative might be between 16 and 16.2. So the remainder after 3 terms has to be less than or equal to that divided by 4 factorial times 0.2 to the 4th power, which is a very, very small number.
If you leave it in that form, you get,
I am fine with you leaving it in that form. Yes. Yes.
What would you do if it was increasing? Should we just take the value at 16.2?
If it was increasing, I'd take value of 16.2. Yes. Yes.
A little confused. Since it's a negative number, the next one is also negative.
Oh.
When the number at the bottom gets bigger,
Yeah, we pretty much always want the absolute error. So just make stuff up. Yeah.
answers on it to the spring 2013 computation.
Oh. Okay. So spring 2013 common page, but I'll try and get them on the fall page as soon as I can.
So yeah, when you plug in 60 for get the maximum error, if you plug in something else, would you also have to change what you're subtracting from 16.2? Like, would you have to change both, or go up some, I guess, to where it was written out as like, yeah, right there.
Oh,
So
okay.
when we plugged in 16 for C, if we plugged in, say, like, I don't know, 16.2, would you also have to change the other 16 in the equation?
No. So this one here is like my A,
Okay. Yeah.
and that's my X, and so I'm only messing around with the C.
So it doesn't have to be the same as this.
No, not have to be the same. So the remainder, the point around which you're doing the approximation, A, that's fixed. And then the thing that you're approximating, that's X, that's fixed. So you just have to find what C can possibly be. Yeah. Is it? Oh. Yeah. Right. Well, that makes it ugly. All right, the comment here was, this is the function we're talking about, and we said it was decreasing, and I agreed with you, but its derivative is positive. Should have paid attention to that. So this is increasing. Which would mean it's bigger than 16.2. Explain that. The derivative here, we pull down -7/2, we get a positive coefficient, x to some power. X is a positive number, so that is a positive number. Meaning the function is increasing. What this would mean, why I don't like that, is that to bound the derivative, we would need to plug in 16.2 here. Which kind of defeats the purpose, because plugging in 16.2 here involves taking the square root of 16.2. So I'll just say this is not a great problem. Well said. But we will do this. 16.2.
I can give you an answer if you really need it.
16.2. I'll put it in blue because they're all the corrections. The 7/2. And what do you get?
Negative 625 times the square root of 5. All over, okay, this is a really huge number. I'm just gonna read it out.
Good digits.
255,09168.
All right, it's that. And so this should go here. we have the bound, okay? Yes.
Could we just leave it in the form of negative 15 or 16?
You could leave it in this form, I would be okay with that. Yes. Yeah.
Doesn't that make the remainder come out negative? Like, does that make sense?
So the remainder could be positive or negative. What we're always interested in, though, is the absolute error. So just absolute value around everything, and that's the absolute error. Yes?
Are we looking for when the fourth derivative is the largest, so like a 16.2 when it's smaller?
No, it would be larger because this function, the fourth derivative is an increasing function.
How do you know it's reading?
Because its derivative is positive. We did the fifth derivative, you'd get a positive function.
Oh, okay.
Yeah, I mean, we have to do the fifth derivative. Yes?
Because the absolute value is the same and
Let me think about this. Oh, this is so messy. Okay. Let me have some quiet. I should apologize for this. I've made a mess of this. Yeah. This is a mess. All right. I'm going to fix this before I post the notes.
Wait, so which one is it?
So do the original. Make this too complicated. My bad. All right. Questions? Any last questions on this? Or move on to a problem I can do better.
So in order to add the error we want, then we'll just take the larger one.
Yeah. Okay. Here's not official math statement, but test taking tip. You're always going to get the one that you can compute. 16.2, that's ugly to compute. 16, you can compute it. That's the one you're going to get on the test, okay? In general, the math explanation is you consider the absolute value of the derivative, and then if that's increasing or decreasing, and then you look at the biggest value. But you guys always get problems that are written relatively nicely, and it should work out that you get the one that's easy to compute. Okay, other questions? Yes. Okay, I'm moving on. Good, all right. Yeah, formula for geometric series. 1A. Only works if you're starting at 0. If you're starting at something else, you have to modify. Other questions?
Wait, you have to
1/3 to the n. Is that?
Yeah, and then if they convert it to 3 halves, it's for 12, but.
Okay. We're going to figure out the limit of this series. Okay. So I can't use my 1 over 1 minus r thing because I'm not starting at 0. Okay, let me write that. Can't use formula on this.
Which formula?
The formula for geometric series. Yeah. But this one, I can. Starts at 0. This is 1 over 1 minus 1/3. Just 3 halves. What's the difference between these two series? I mean, the actual, like, difference, a number. Yeah, the difference is the sum of the guys between 0 and 4. 1/3 to 0, plus 1/3 first, plus 1/3 squared, 1/3 cubed. So, a equals 4 to infinity of 1/3 to the n is 3 halves minus all these guys. That makes sense? Yeah.
Why can't you just make the a term the fourth term?
A term the fourth term?
You make the formula a over 1 minus r, and you make a the fourth term, it works out the same way.
It's like a lot easier because you don't have to do the mistake of all the arithmetic.
Okay. Yes, you can do that. So you could also say a equals 0 to infinity 1/3 to the. I guess I'm mixing up my k's and my n's, but everyone, no one's. What? I mean, like here. This should be a k, but no one seems to be thrown off by that. So. What?
We're
If you
saying
make
you
A
raise
equal to 1/3 to the 4.
You literally just
A
take
is
the
just
point,
one.
and a is just the fourth term.
So A is always going to be different.
Yeah. And then to find it, you just do a over 1 minus r. So it'd be 1/3 to the fourth over 1 minus 1/3.
Yeah.
You get the same thing.
Okay. Okay, sure. So this works because you could just take this guy and factor out 1/3 to the fourth from every term. And that becomes your A. And then the rest of them is like starting at 4. Should I write that out? All right. I'll just write it down. There are review sessions. There was a review session tonight, not me, but someone else.